Okay, guys, we're doing a second video about mass and energy equivalence. Okay, so we need to introduce the unified atomic mass unit first. Last session, if you remember, we introduced a new unit for energy as 1 eV. And 1 eV is a very small amount of energy. So why do we need to learn that 1 eV? Because the energy involved for nuclear physics in a nuclear level is very small. So that's why we use 1 eV. We use eV 1 mega eV as our energy unit rather than joule. Okay, and here we're going to use a similar approach but for the mass. Okay, so normally what common units we are going to use, what common unit we use. Normally for mass, the units we use are gram, kilogram, okay? Right, but now we are going to use another unit, which is unified atomic unit, okay? So the definition, one atomic mass unit, 1U, is 1/12. Okay, 1/12 just means 1/12, the mass of a carbon-12 atom. Alright? Okay, so is 1/12 of the mass of a carbon-12 atom. So how could we calculate that 1U? Okay, so for here, it's only for chemistry student. So if you are not chemistry student, possibly you don't understand what I'm going to talk about. I'm going to show you how to find the magnitude of 1U. But that's okay. If you don't understand it, it's completely fine because that's just for chemistry student. Okay, and how could we calculate that 1U? Okay, so let's see, because that's 1/12 a carbon atom, so we use 1 mole of carbon atom divided by Avogadro constant. So Avogadro constant means number of atoms in in 1 mole, right? Okay, so let's try to do this one. Okay, so mass of 1 mole of carbon atoms actually 12.011 gram divided by 12 is because of 1/12 times Avogadro constant, that's the constant, Avogadro constant, and you will get the number as 1.66054 times 10 to the power minus 27 kilogram. Okay, so as you can see, the number is really small. Okay, so that's why we are going to use these units, because we are not going to use kilogram or gram for the calculation of nuclear masses, because they are just too huge for nuclear physics. Okay, and the idea is the unified mass units are often used for very small mass involved in nuclear transmutation, very small mass. Okay, remember that. Okay, to convert between kilogram and U, if you got kilogram, you try to convert into U, you need to divide. Otherwise, on the other hand, from U to kilogram, you multiply. Okay, and for kilogram to U, of course, your number should be much greater than before. From U to kilogram, your number should be much smaller than before, because U is such a comparatively super small than kilogram. Alright, so, and this table is quite useful because it gives us some very common masses of the particles, but not only in kilogram but also in terms of U. Okay, when we compare the mass in U, so normally in chemistry or in the science you've learned in your year before this year, possibly in year 10, year 9, you normally we treat mass of a proton, mass of neutron, they are the same. But actually when you see that they are not the same, neutrons are a bit heavier than proton, right? So when you compare up to the 4th unit, they are different. Okay, so that's why for this chapter, normally when we use numbers, we use such a long string of numbers because we need more silicon figures to see to see precisely how large, how small the numbers are. All right, and also I give you the electron positron, the mass of them is so small. All right, the only mass in terms of U is exact is carbon 12 because that's exactly how we define 1U. Okay, U is defined by 1/12 of one carbon atom. Okay, so that's why for carbon 12 the mass in U is exactly 12U. Okay. Okay, that's why what we have said. Okay, to see the effects of mass defects, you need to base our calculation up to at least 4 silicon figures. All right. So let's see if we apply that formula. Okay, possibly let's write this one as well. Still remember this is the famous energy mass equivalence. Okay, it says during the nuclear reaction the mass is going to be smaller because there's some loss in mass. Okay, the loss in mass converts into the energies of the emitter particles or the emitter radiations. Okay, so the calculation relates that emitter energy and the loss in mass or mass defect is delta E equals delta M times C squared. All right. Okay. So let's see how large is the energy equivalent to 1U. Okay. So energy equivalent of 1U. Okay. So we use this formula 1U times. Okay. So that's the speed of light. Okay. U is that mass. We have just got it before. And when you calculate them, okay, so in terms of joule, it's really small. It's really small. So that's why we don't prefer joule. In terms of eVolt, it becomes too large. Okay, so we use mega eVolt. Okay, so the number is more manageable. All right, so that's around 931.6 mega eVolt for 1U of matter. So if during a nuclear reaction, if you lose 1U as mass, that will produce. Okay, so let's see this question. It's about how to convert unified atomic mass units into other units. So radioisotope for Iron-52 has a mass of that many U. Okay, so you need to be very careful about the unit by now. Okay. So if that's U, that means they are using atomic mass unit, unified atomic mass unit, all right? And write this mass in kilogram. Okay, so you need to write the mass into another unit. Okay. Okay, so remember that the reference is we can go back to see the table. So during the examination, you are going to be provided by the constant of 1U, which is 1.66054 times 10 to the power minus 727 kilogram. Okay, so if you want to change that number, change the mass in U to kilograms, simple, because you just multiply that number, that will do it. Right, so let's say if I see this number, okay, because that number is just too long, I don't want to copy it. Sorry for I just use the advantage of copy and paste, right? Okay, so I'm going to use this number. Okay, and I'm going to take away that, sorry, I just replace that U by that constant. Then that will do it, right? And what do we have now? By doing that, it should be, okay, let me check the answer. It should be 8.62619 times 10 to the power minus 26 kilogram. Okay, such a small mass, right? So that's why we don't prefer to write in kilogram because it's so small. Calculate the mass of this one, so boy, in kilogram and U. Okay, so that some confusion might be here. So it's about Fe. So what do we mean by Fe? If you are good at chemistry, if you still remember that, Fe is the symbol, which is the atomic symbol for iron. So actually they are talking about the same radioisotope, but they use another symbol, use Fe. Okay, so Fe 5226. Okay, so why do they give you that one? Okay, you need to see this radioisotope for iron has mass. So this mass is for the radioisotope. So radioisotope is what? It's kind of an atom. So it's an atom. But here you're going to find the mass of nuclei. Okay, so atom and nuclei, they are different, right? Nuclei means we're going to calculate the nucleus. The type of nucleus called nuclide, right? So you can't say, okay, we have done that because we found the mass of iron 52 in terms of kilogram, and also it's given by you. So why do I need to recalculate that again? Okay, so be careful, because this time you are going to find the nuclei. For atom to nuclei, you need to take away the mass of what? Electrons. Okay, because atoms means nucleus plus the orbiting electrons, right? Okay, so that's why for this mass, for the nuclei, okay, for the nuclide, for the mass of nuclide, of that's Fe 2652, you need to use mass of the atom, that's one, minus how many electrons? Okay, so that 26, that means 26 protons. So we know the number of protons and number of electrons must be the same. So 26 electrons, mass of electrons. Okay, sorry for my handwriting. Okay, so at least it's readable, right? Okay, so that's how you could find the mass of nuclei. I need to emphasize that again. Okay, so that three things, right? Okay, mass of the atom, we have found it in terms of kilogram, or in terms of U. Possibly we might need to find that's in terms of U first. Okay, in terms of U, again, let me to use that again. Okay, mass of this one is minus, okay, what's the mass of electrons? Let's go back to a previous page. Okay, let's go back to our previous page. Should be here. Okay, so here we know that mass of electron is this one. Okay, we're going to use one for U. Okay, this one. So that's the mass of electron in terms of U. And how many of them? There are 26 of them. Okay, so here's the formula. Alright, so after you take away and you do all the calculation by your calculator, it is that many U. Okay, and you have to change that mass in terms of kilogram. Okay, so in kilogram, mass would be this one times the mass of 1 U, right? And that will give you, okay. Alright, okay, hopefully that makes sense, right? Okay, so that's another part. I add this part because that will help you to do your homework. Calculate the energy will be released if iron 52 suffers 0.1% of mass defect. Okay, so if that's mass defect, why there would be energy released? Because we know mass defect will turn into energy released, right? So we are going to use Einstein's formula. So that's an Einstein formula. Okay, right? So delta M is 0.1% of mass defect in a nuclear reaction. Okay, so the mass, of course, we are going to use a nuclear mass, not the mass here. Okay, because that's the mass for the atom. We are now going to use the mass of the nuclei. Okay, so mass of the nuclei should be, okay, mass defect is only 0.1% of this one. That's the mass of nuclei. Okay, right? And oh, sorry, I need to copy it. That looks better, right? Times, okay, and times c squared. All right. Okay, so what we're going to do? Okay, so that means 0.1 divided by 100 times this one. Okay, let's see this one. What does it mean? It means U times C squared. It means the energy, I might use another color, energy equivalent to 1 U mass defect. Okay, have we got that before? Yes. If you still remember, just turn back to the last page. Okay, in the last page, we have calculated that energy equivalent to 1 U. That's just 1 U times C squared, right? So that's just 1 U times C squared. Let me emphasize that a little bit more. 1 U C squared would be equivalent to 931.6 megaevo. Let me copy this number. Okay, and I'm going to place that number here. So we are going to use this as a 1 U C squared equals to this one. Okay, right. So then use your calculator. We do the first part of calculation first. Right. Okay, that would be 0.1. Okay, I need to use my calculator. Yep, you use yours. Okay, so here you will have for the first part of times U C squared. That means 931.6 megaevolt. Okay. Okay, so that's what you are going to get. That's 48.3816, okay, megaevolt. All right, so that would be the answer. Alright, that makes sense. Okay, remember this part is not in the textbook. Okay, so even you go to the e-reader of the textbook, you won't find this. That's added by me. Okay, but that part is will be relevant to what you are going to do. Okay, so this is your homework, one of the homework, right? Okay, so again, here is the homework. Please photo to homework folder. I'm going to tell you every time. All right. All good. Okay, so it will be similar. Try to do it. Okay. So the next thing is about binding energy. So binding energy. So when we look at the question, it seems it's related to we get something binding together, but actually the definition of binding energy is about how to disassemble, how to separate, how to split up a nucleus, right? Okay, so that's the definition of the binding energy. Okay, the key word is the binding energy of a nucleus. It's about the nucleus. It's the energy required to disassemble. Disassemble means, okay, split up or disintegrate in completely into its constituents. Okay, let's use an example. Okay, so a nucleus, for example, helium-4 is a nucleus with 2 protons and 2 neutrons. Okay, and when you disassemble them, they become 2 neutrons and 2 protons. These are called constituents. Okay, these are called constituents. Okay, these are called constituents, or they are constituent nucleons. Okay, so can helium-4 just split up like this? Of course, it can't. So that's why you need to add some energy, and that energy you give it to helium is called the binding energy, so that it enables helium to be disassembled. Otherwise, helium-4 won't be disassembled. Okay, so for the current equation is a energy absorbing equation, because you need to provide the energy for the whole equation to happen, right? So for this direction, it can't naturally occur. Okay, from this side, okay, from this direction, we say no, because you need to add energy to it. So that means it can't happen naturally. Okay, can't happen naturally. That means if it does happen, it must come from artificial intervention, right? So that means artificial. Okay, artificial intervention. Okay, you need to intervene to let it happen. Okay, but how about if you go for another direction? For example, how about this direction? So for this direction, because if we release energy, because you need to give nucleus binding energy to separate apart. So for those being separated, join together to form the helium, to form back the helium nucleus, and this process you will release energy. Okay, so in this time, this can occur naturally because it's energy releasing. Okay, so any reaction which can release energy, it can be it can occur naturally. Otherwise, it can't. Okay, right? Okay, so let's see. According to Einstein's mass-energy relation, the mass of a nucleus must be greater than or smaller than the total mass of the constituents. Okay, let's think about this. This is very important, okay? So, which size has the greater energy? I mean, helium-4 or their constituents, the total mass of their constituents. Okay, so in chemistry, we think, okay, if you separate the helium-4 into 4 constituents, nucleons, then their mass should be conserved, right? But that doesn't happen in nuclear physics. Remember that everything happens in nuclear physics, the mass will be changed. Although it's very slight, it's still changed. Okay, so the problem is which side will have bigger mass. Okay, so remember, whenever it's naturally occur, that must be mass defect. Which direction is going to be naturally occur? From right to left, from constituents to the nucleus. Okay, so for this side, I mean from right to left, there would be mass defects. If there's mass defect, means the total mass of the 4 constituents would be greater than the mass of heliums, right? So that means the mass of the nucleus, that's on the left hand side, must be smaller, okay? Smaller than, okay? So that means from the nucleus to their constituents, there's no mass defect because the mass from smaller to bigger. Alright? So that since there's no mass defect, that means this will not happen naturally. But from constituents to the nucleus, okay, the mass becomes smaller. Okay? So there will be mass defects. Alright? So the only naturally occur is from constituents to their nucleus. Okay? Not the other way around. Okay? Okay, remember this, the mass of nucleus must be smaller than the total mass of constituents. The mass defects convert into binding energy. So binding energy will be equals to the mass defects from constituents to the nucleus. Okay? Let me give you another visual illustration. For this one, you see which side is their constituents. Of course, this side. Okay. Okay. So, okay, constituents. Okay, so that's a constituent. All right. For this is the whole nucleus, just the complete nucleus. Okay. So, which side is heavier? Okay, this side is heavier. You see, because it's lower, that means this side is heavier, and this side is lighter, right? Okay, so that means the nucleus is lighter than the constituents. They are constituents, so it's constituents. So that's true, right? Okay, good. And their difference in the mass will becomes the binding energy. So that's how the Einstein's equation suggests. Alright, so too much on this. So let's move on. Okay, let's do one calculation. If I'm going to find the binding energy of lead, that's Pb is called lead 20682, how could we do it? Okay, so I got some information. I got the information that's mass of proton, mass of neutron, mass of the nucleus. Okay. Be careful this one. This one means the whole nucleus, not their constituents. Okay. So the mass of nucleus 205969 U. And how could we get the mass of their total mass of their constituents? Okay, total mass of the constituents. Okay, so of course we need to know how many protons. Should be 82 protons. So my mass of protons plus how many neutrons? 206 minus 82 mass of neutrons. Okay, so that's the total mass of the constituents. Okay, let me substitute the numbers. Alright, so that's the total mass of constituents. So let's compare with the mass of nucleus. Which one's heavier? Okay, constituents. So that's correct because we always know that. Okay, the total mass of constituents should be greater than the mass of nucleus itself. Alright, so let's find the delta mass is this one. Take away. Alright, okay, so, okay, sorry. I'm running out of space. Okay, so that's 1.704. Remember the units? Okay, then you need to calculate the binding energy. So binding energy is just kind of changing energy, which you can use delta M times C squared. So delta M 1.704 U. Okay, remember that's UC square is equivalent to 931.5. Sometimes they give you 931.6. That's okay. So possibly I need to change that for the consistency. Right. So that's 1.704 minus 931.6 mega evolt. Okay. Alright, so that's what we get. Mega evolt. Okay, so that's the binding energy. That energy means if you want to disassemble the whole nucleus, you need to at least apply that amount of energy to the nucleus. Alright, so let's see. If a nucleus has a mass number A, atomic number Z, and the binding energy B, alright, okay, and you got the mass of neutron, mass of proton, speed of light, okay, which one can you calculate the mass of the nucleus? Okay, so remember that mass of nucleus would be less than the mass of the constituents. Okay, so mass of constituents. Constituents. Okay, take away the mass of nucleus equals, that's delta M, right? That's delta M. Okay, and delta M, if we use the formula that's binding energy equal delta M times C squared, just change the subject, and that's delta E. In this case, they use B as a binding energy. Binding energy is B, so that B over C squared. Okay, so you see, if I'm going to find the mass of nucleus, how could we rearrange the formula? I should rearrange formula like this: mass of the nucleus equals mass of the constituents. Sorry, my handwriting. Take away this one. Okay, so how about mass of the constituents? Mass of the constituents would be number of proton times MP, and number of neutron times Mn. Okay, number of protons should be Z, number of neutrons should be A take away Z. So which one would be the answer? This one. Okay. Right. So that's a multiple choice question, quite interesting. So I bring it to you. Okay, so another calculation we are going to be interested is about the binding energy per nucleon. Okay, right. So, but I'm going to do that on next video. Okay, because I don't want each video to be too long. Okay, so you just stop now. You can go back to do some of the homework or try to understand the previous session, and we'll go back to finish this chapter. Okay, see you next time.